So the main goal with which we started out the entire Fourier analysis is to simplify our convolution process, right, in order to find out the output of an LTI system. So how is Fourier series at the end of all simplifying this convolution operation? So we'll put everything together that we have seen so far. So given any signal, let's say we are given a signal z of t, and we are feeding this to an LTI system whose impulse response is h of t, we want to find its output, which is this convolution operation. And all this analysis we did so far, we know how to decompose the given periodic signal into its harmonics with some fundamental frequency, and we know how to find out the coefficients of these harmonics. So that is what Fourier series tells us. So we have the Fourier series representation, and the other thing that we also know and which we exploited a lot is that the sinusoid, the complex sinusoid, is the eigenfunction of the convolution operation, which means when you feed in a complex sinusoid to any LTI system, the output is the same sinusoid just scaled with some scalar. That is what we know. This we already know, which means if I have a sinusoid of frequency omega, if I feed that into any LTI system, I will get the output to be the same sinusoid scaled with some factor which is a function of the frequency of the sinusoid, and how to compute that scaling factor, which is basically the eigenvalue. So you compute that through this projection, right? This is basically again something like an inner product for signals. You take the impulse response, project it onto the eigenfunction, and you compute this eigenvalue. So if you know these eigenvalue and the Fourier series coefficients, all you have to do is just multiply them together. Okay, so this is like you have convolution in the time domain, and in the Fourier series coefficient, all you have to do is just multiply the coefficient with this eigenvalue, and then you are done. You will get the output in the Fourier series representation. So all you have to do here is now multiplication of the Fourier series coefficient with the eigenvalue of the corresponding sinusoid. So why is this true? So all you have to do is just substitute this back here. So if you see this convolution operation, what are we doing? So you just convolve this entire representation here, just substitute and we know that convolution is distributive and it is linear because of all these properties. You can now rewrite this in this form. This is because of the properties of convolution. It is distributive and it is all linear because it is an LTI system. And now essentially what we are doing, we are just simply convolving the impulse response with the complex sinusoid, which is the eigenfunction of convolution, which means we can replace this entire convolution here with lambda k omega and e power j k omega t, and we will get the output. So the output now simply becomes multiplication of the Fourier series coefficient with the eigenvalues of this system. So the eigenvalues of this system you can compute without even knowing what the input is. The z of t, I need not know what z of t is. Even before knowing what the input is, when I am designing the system itself, I can tell you what these lambda omega is going to be, the eigenvalues are going to be, because all I need to know is the impulse response and nothing else. I need to know the impulse response, and for every frequency that you can think of, you can find the corresponding eigenvalue here. So which means I can compute these lambda omegas only once in my entire lifetime and then store them, and I can keep reusing it. I don't have to compute it again and again when the input changes. So all I have to compute when the input changes is the corresponding Fourier series coefficient here, and then simply multiply with the eigenvalues that you have computed and stored, and then find the summation. This is much simpler compared to the convolution operation where you have to take the signal, flip it, keep shifting it, multiply, find the area at every point. So that's way more complicated compared to this. So this is much simpler In fact, this is several orders simpler when it is implemented in real life. Many computers in fact implement the computation of the output of LTI systems through this technique rather than actually doing the convolution. So, this has simplified even not for computational purposes, but even for analysis purposes. You just have to multiply a set of scalars and then you get the output. So, even for us it becomes much simpler to analyze this, and we can also infer a lot of things from this. So, remember when we said you convolve two different signals, the length of the signals may increase, but what happens to the frequency content? So, what if I convolve a signal which has some amount of bandwidth, and if I know the bandwidth of the impulse response of the system, or if I know what the impulse response is, can we tell what will happen to the output of this convolution, assuming this is an LTI system? In fact, we can say for sure by looking at this. So, what does this mean? So, if I have a non-zero AK, when will I have a non-zero AK? If I know that the bandwidth of the system is some B, if the bandwidth is some B radians per second, okay, then K omega should be less than B, okay, mod K omega should be less than B. Only then the corresponding AK will be non-zero. That is the definition of bandwidth, it follows from bandwidth. So, if a particular AK is non-zero, then it means that this product AK lambda K can also be non-zero as long as this is not zero. Both of these should be non-zero, only then the output, the multiplication of these two coefficients will also be non-zero. So, it means that the bandwidth of the output will never be greater than the bandwidth of the input. So, this is a very interesting insight that we can get from this analysis. This is not really apparent from convolution in time domain, but if you see the equivalent of the convolution in the Fourier series coefficient, it becomes very clear that the bandwidth can never increase at the output of an LTI system. At best, it can only decrease. So, if this lambda K omega is equal to 0, then that frequency is driven to 0. So, which means the bandwidth can reduce. But when AK is equal to 0, this product is always equal to 0, which means if the bandwidth is B, then you can never have a bandwidth which is greater than B at the output. So, this is very interesting. So, the coefficients determine what is the output's frequency components. So, if this lambda K omega is 0, then the corresponding frequency is not present at the output. So, let us say the output is some y of t, then the y of t is also periodic. So, remember there is another property that we saw earlier. If input is periodic, at the convolution's output you will always get a periodic signal. So, y of t is also periodic, which means you can decompose y of t also in terms of the Fourier series. Okay. So, let us say our coefficients are Bm here, and now what is the Fourier series coefficient of the output? It is related to the input through this relationship. It is Am times lambda m omega, or we can keep everything in terms of K. So, this is the relationship between the input output Fourier series coefficient. So, the eigenvalue of the LTI system determines what are the frequency components that will be present in the output. If the eigenvalue of a particular frequency component is 0, okay, for the LTI system, then the output will also not contain that particular frequency component. So, this is what we refer to as the frequency response of the LTI system. So, if the eigenvalue is 0 here, then the LTI system can never produce this particular frequency at the output. So, if I feed in this particular frequency at the input, the response of the LTI system is 0. It will not produce it at the output. So, if it is, let us say, non-zero, if it is, let us say 2, then the LTI system will actually amplify this frequency by 2 times. If it is, let us say, 0.5, then it will attenuate this particular frequency by 0.5. So, this is how it responds to a particular frequency. So, these eigenvalues of a particular complex sinusoid of a frequency omega is what we refer to as the frequency response of this LTI system. In fact, what we can do is we can plot this as a function of omega. So, you change omega. For every value of omega here, you evaluate this integral. Remember, we can evaluate this without even knowing what the input is, okay, and then plot this integral, plot this value. For every value of omega, you will get one number here. It can be a complex number, of course, it need not be a real number always. It can be a complex number, it can be a real number, whatever it is. You can just, if it is a complex number, what it means, the magnitude tells you by how much the frequency is amplified or attenuated, and the phase tells you by how much the frequency's phase is changed. So, if I have a sinusoid of 10 hertz, then if the frequency response is a complex number for that frequency, it means that, let us say the complex number is j, okay, the lambda omega value is j, then it means the magnitude is 1. So, there is no amplification or there is no attenuation, it passes the frequency as such in magnitude, but then it multiplies the phase with j. If you are multiplying the phase with j, what does it mean? It means it is a rotation by 90 degrees, right. So, it changes the phase by 90 degrees. So, this is what it means if there is a complex number as the frequency response. So, for every omega, you can evaluate what this lambda k omega is. Of course, when you visualize it, it is going to be a complex signal. So, you have to visualize it with a magnitude plot and a phase plot, or with the real part and the imaginary part separately. So, it may look something like this. So, what does this mean? So, if I feed in a frequency of omega equal to 0, then lambda 0 is this much. So, if I feed in with omega, let us say 10, then lambda 10 is this much. So, let us say if our signal looked something like this, then if there is omega equal to 20 here and lambda 20 is 0, then it means that this will not pass any input which has a frequency of 20, meaning if I feed in a signal whose a 20 is non-zero, the output will have P20, which is equal to A20 times lambda 20, okay, assuming of course here omega is equal to 1, then this is always going to be 0 no matter what the value of A20 is. So, the LTI system effectively filters out frequencies for which its eigenvalue is 0. If the eigenvalue is 0, it completely removes those frequencies of the output. So, this gives us an idea of how to identify or how to characterize filters. So, if I plot the frequency response of filters, from this frequency response I should be able to say that, okay, my LTI system is going to filter out these many frequencies. It is going to attenuate this much frequency by this much, or it is going to amplify this much frequency by this much. So, this becomes a very, very important tool to analyze circuits and filters and their characterization. The two famous LTI systems that we started out with is the differentiator and the integrator. So, if we analyze the frequency response of these, how does it look like? Or if we want to know how does the differentiator and the integrator affects the Fourier series coefficients of an input periodic signal, then how do we analyze that? So, that is what we will see in this slide. So, if I have a signal z of t which is periodic, then we will decompose that using the Fourier series coefficients like this. If we pass this through an differentiator, what happens at the output of this differentiator? It is very easy to see because we already know these coefficients are the eigenvalues, and these complex sinusoids are eigenfunctions of the differentiator and integrator operation. So, if I just integrate or differentiate, let us say we are differentiating this. So, if we differentiate this, then what do we get? You get AK jk omega times e power jk omega t. So, the output of the differentiator now is of course another Fourier series. We can decompose the output using Fourier series representation again. So, what is the Fourier series coefficient of the output? It is nothing but the same as input, but multiplied with jk omega. So, this is the relationship of the Fourier series coefficients of the output of a differentiator and its input. Now this tells us something very interesting. So this tells us the coefficient now is a function of omega. So what happens when omega is 0 here? If this omega is 0, then pk is 0, and if this omega is a very large number close to infinity, then this bk is also tending to infinity. So we can find the frequency response of this directly by finding the eigenvalues. So how do you find the eigenvalues lambda omega? We know that for the input e power j omega t, the output is going to be its derivative, which is j omega times e power j omega t. So this is our eigenvalue. So we have found out the eigenvalue. So if we plot this eigenvalue, how does it look like? So if we plot this eigenvalue, then it looks like something like this, right? So this is, of course, we are going to plot the magnitude here. So this clearly says that if my frequency is less than 1, then my amplitude or the magnitude with which I will pass them is going also less than 1. So there is an attenuation for frequencies which are less than 1, and for everything that is greater than 1, you are going to amplify it. So this is like an high pass filter. Of course, this is not ideal. An ideal high pass filter will look something like this, right, where below a particular frequency, let's call some omega c, below that it's all going to be 0, and above that it's all going to be 1. So this is what we refer to as an ideal high pass filter, but this is something like an high pass filter which is not ideal but has some response which is similar to a high pass filter. It does not treat all frequencies equally. Lower frequencies are attenuated, higher frequencies are amplified, and hence we call this as a high pass filter. Okay. So a differentiator is a high pass filter. Now what about an integrator? So let's try and do the same thing. So what if we feed the same eigenfunction to the integrator, right? What happens at the output? If we feed something like this to the integrator, then of course you see 1 by j omega e power j omega t at the output, which automatically means our eigenvalues are going to be 1 by j omega. If your eigenvalues are going to be 1 by j omega, then what is your frequency response? You plot this frequency response as a function of omega. Of course, we will plot only the magnitude here. So if you plot the magnitude, you will see something which is like this, a hyperbola, right? So what does this tell us? So this tells us that the lower frequencies have a very high amplification. As omega becomes smaller and smaller, this magnitude becomes larger and larger, and as omega tends to infinity, this magnitude becomes 0. So it's the other way around, right? So what happens to the output of the integrator? So if you have an output, so we'll redo this entire thing. Now we'll take a periodic signal, decompose it in terms of the Fourier series coefficients, pass it through the integrator. So we have something like this, which means because of the eigenfunction properties, you get ak divided by j omega k times e power j k omega t. See, we didn't have to do any integration, we didn't have to do anything. Eigenfunctions are so useful. No convolution, nothing. You can directly write like this. So now the relationship between the input-output Fourier series is like this. So as in this case, as omega tends to 0, bk tends to infinity, whereas as omega tends to infinity, bk tends to 0. Okay. So, or at least the magnitude of these things tends to infinity and 0. So, what this tells us is this behaves like a low pass filter. All the lower frequencies are amplified and higher frequencies are attenuated. Once again, this is not an ideal low pass filter. We know that an ideal low pass filter looks something like this. So, you have a cutoff frequency, everything below that is passed off without any attenuation, everything after that is cut off. This is what we would ideally expect from a low pass filter, but of course the integrator is not an ideal low pass filter, but it is some kind of a low pass filter. So the differentiator is a high pass filter, integrator is a low pass filter. and the output of the Fourier series coefficients of these two LTI systems are simply nothing but the multiplication of the input Fourier series coefficients and their eigenvalues. The eigenvalues of these systems are just j k omega either multiplied or divided.